Here's an applied optimization problem. A right circular cone has a volume of pi thirds r squared h and surface area s equals pi r square root r squared plus h squared. Find the maximal volume achievable with a surface area of 2 square meters of plastic. So you have a cone. What it means by right circular, the base is a circle, right? It's a right angle. The radius and the height form a right angle, okay? And we know that we've got 2 square meters of plastic. That's how much we get to use, and we're trying to get as much volume in that cone as possible. So we're going to have to figure out R and H so that we can fill up that, we can make a cone of that shape. Okay, and make it with the maximum volume. Okay, so here we need to solve that for one of the variables. Then we're going to plug it in here, take the derivative of V. Since R shows up twice and H only shows up once, let's go ahead and solve for H. So 2 over pi r equals the square root of r squared plus h squared. It's nice that we know r and h are both positive, so we don't have to worry too much about pluses and minuses. Let's see, we're going to square this. So 4 over pi squared r squared equals r squared plus h squared. That means h squared equals 4 over pi squared. I think I'm going to write this because we're taking the derivative as r to the negative 2 minus r to the 2, moving that to the other side. So h would be the square root of that thing. Again, only the positive root since h is positive. I'm going to take that and I'm going to put it into this volume formula. So volume equals pi thirds r squared times the square root of this piece right here, 4 pi squared r to the negative 2 minus r squared. Now you could take the derivative right there. You'd have to use a product rule and a chain rule, but frankly you can skip using the product rule if I can get that inside the square root. Well, I happen to know that r squared is the same thing as the square root of r to the 4th, right? Square the inside, square root the outside. Now, I can actually combine it with the thing to the right. So I'm going to multiply the things to the right. That times r squared, that times r squared. So I get pi thirds square root of 4 over pi squared. R to the 4th, r to the negative 2 comes out to r squared. R to the 4th, r to the 2 comes out to r to the 6. Okay, now if that's V, I'm ready for the derivative. The derivative is pi thirds. Now I'm going to use the chain rule. This is all to the 1/2 power, so 1/2 inside piece to the negative 1/2. So let's see what we have there. 4 pi squared r squared minus r to the 6th times the derivative of the inside. Let's see. This is 2r, so that all comes to 8 pi squared r minus 6r to the 5th. Okay? Now that's the piece that I need to make sure is not equal, or, well, I need to see where it's equal to 0 or undefined. So let's see. If I've got that equal to 0, first off, I can cancel these terms. I can multiply by the reciprocal of them. This is in the denominator, right? So really what I have here is I have, let's see, I can factor out a 2 and an r from this right here. So I have 2r times 4 pi squared minus 3r to the 4th. This is in the denominator and in a square root sign. Let's see, so I guess I can factor out an r squared. Now you can have an r squared out there or an r right here. So that's 4 pi squared minus r to the 4th. Okay, so notice the r over r, those more or less cancel. They perfectly cancel as long as r is not equal to 0. You could say that you have a critical point at r equals 0, but r equals 0 is not really going to maximize any sort of volume at all. So what we're really concerned about is these two inside places. The derivative is 0 at, let's see, where 4 pi squared equals 3r to the 4th. Let's see, so we divide both sides by 3. Now, if I took the square root of both sides, I'd have 2 over root 3 pi and r squared. Then I take the derivative again. R equals the square root of 2 over root 3 pi. So that's about as probably as neat as I'm going to get that critical point. The other critical point is a place where the derivative is undefined. Let's see, what do I have here? I have 4 pi squared equals r squared, r to the 4th. Let's take the square root of both sides. So I have 2 pi equals r squared, where r equals the square root of 2 over pi. So that's a critical point also. Just to see, remember, we are maximizing the volume. So I'm going to use a first derivative test. Let's see. I know the derivative, which one of these is bigger? Let's see. This one has a smaller denominator, so that means it's bigger. So we've got the square root of 2 over pi. We've got the square root of 2 over root 3 pi. The derivative is 0 there. The derivative is undefined there. Let's see, what happens in between those points? Well, if we had something smaller than this, let's see. So this denominator, let's see, if we have something that's smaller than this point, this is a place where this is 0. As r gets smaller, now notice this term is less than 1, right? At 1, the numerator and the denominator would be the same. So this term is less than 1. So as r gets smaller, this term gets smaller. That means this becomes positive, right? So we have positive. Then as r gets bigger, this term is getting bigger, so the numerator becomes negative. This term is still positive at this point, negative. Past that point, let's see, what happens past that point? Past that point, we have something that is undefined. So that seems to be the end of my domain right there. Okay, so that says this is the local max.